Ferdousian, this is my partner Mehtab, Dhillon, and our project is the musical lights. So musical lights or dancing lights are basically popular because of their commercial use in nightclubs, parties, Christmas lighting actually. And what these products that are out in the market right now, they have one thing in common, and that is that the lamps in them, they turn on and off based on a pre-program that's already installed in them. So they're basically pre-programmed to do that in a pattern of basically, let's say, a light is supposed to just like turn on for 2 seconds and then turn off. So it's basically pre-programmed. What we wanted to do is come up with a product that the consumer can actually sync their own music to it, their own audio input into it. Actually, we wanted to build a system that they can plug their music into it, and we also wanted to control the intensity of the light. So to reach that goal, we came up with this design. This includes our amplification circuit, our AC zero crossing detector circuit, dimmer circuits here that are connected to the light, and basically our microcontroller. I will basically go over all these, well, actually most of these items here. I'm going to start off with the microcontroller. As the audio input is fed into our microcontroller, at the same time, we're getting a sharp pulse because of our AC zero crossing detector. At basically every wave that crosses the zero, we send a sharp pulse. So when this is fed to the microcontroller is supposed to separate each frequency into different bands and perform FFT on them. And once it does that, because of this sharp pulse here, we create a new pulse. This pulse would have a width that is varied based on the different frequencies that were divided already. So once we reached that goal, we wanted to build a circuit that does that for us. Based on the width of these pulses, we could control the dimming of these lights. So we built our dimmer circuits. And this is basically a schematic of our 4-channel of dimmer circuits, which is actually built inside that box. So I will explain how this dimmer circuit works. Once the pulse with the varied width enters our circuit, this is our opto-isolator. It triggers this on. There are many functions of this opto-isolator. One is to actually electrically divide our high and low voltages, our high being the 120 AC volts, and our low being the low level of DC volts from our microcontroller. So after that, basically, once the opto-isolator also has a diac inside of it and an LED. Once the LED is on because of this pulse, a diac is triggered on. Once the diac is triggered on, we can actually control the on and off switching of this triac over here. The triac is a switch itself. It's a 4-layer PN junction solid relay switch. And basically, depending on the width of this pulse, we can control how long this triac is on. And based on the time that it's on, we can actually control the amount of AC voltage being supplied at each cycle. So we built this circuit and we wanted to test it. At first, we had not introduced the zero crossing circuit yet, so all we had was the dimmer circuit. We took that in the lab and we actually hooked it up to a pulse generator and we gave it a square wave. And by hand, we actually played with the widths of the pulses to see if the lights would dim. But the results were negative. We actually did not see any of the lights dim. We actually saw them flickering. So we wanted to fix this problem, and now Mehtab will explain how we fix this problem.
To fix the problem of the flickering lights, we use the zero crossing detector circuit. The basic aim of the circuit is to sync the light lamps with the zero crossings of the AC voltage. This is the schematic, which consists of a transformer. In the transformer, we get a full wave rectified 6 volts DC, which is supplied to a voltage regulator, from which we can get a pure 5 volts to power the other circuits. And we have another one, there is 3.3 volts to power the memory controller. The 6 volt rectified, full rectified DC 6 volt voltage is then supplied to a LM393, which is this whole thing. This acts like a comparator. It compares the 6 volts with a very low level voltage close to 0. So for the timing, when the voltage is below that level, a pulse is generated for this very short period of time. So right here, we generate a pulse which is of a very short width. But it has a curve, it's not sharp enough. So send it to another block, where it's again, the output of this, the output that we get to the next block is a pulse which is very sharp and steep.